differential. OK， 那我们开始吧。上次我们介绍了同调群，然后链户型和边界算子，so 今天继续讨论这个同调群。So last time, we talk about链户型，然后我们用例子计算这个同调群的例子。这个是边界算子，盲子del square is equal to 0， 然后同调群我们可以定义，kernel of the 便捷算子mod image of 算子。So and then this one is often called cycle, Q cycle. And this one is called the boundary. 我们介绍了这个单曲映射是K prime is the 单曲 and then so the K0 prime. So the point is mapped to point. And also we need to have the we need to have the point is mapped to, and also root A0 AQ is the simplex in the K. Should be also simplex. It's also simplex. Okay. So 如果这个 A0 AQ 是单群，单群的话，这 A0 FAQ 是应该是单群。So 比如说 ，so you can map to A0, A1, A2, A3, and here is the A0, A1 is here, A2, A3, and is equal to A0. So if this triangle, this 三角形 is mapped to 这个两边两个龙 So if this is the how say this triangle is mapped to these two edges, this is not this is no longer the simple channel. This is no longer simple channel. That's what I drew this last time. Okay. Okay. And this will induce this simulation map will 诱导这个 chain complex chain function 的映射。So if you have the if the FAI is not FAJ, so any I is not J, otherwise it just maps to 0. Otherwise. Okay, so like this. Now, for instance, if this is the case, this is a chain map, a simple chain map. For instance, A2 and A3 are mapped to FA2, FA3. So this is the just it induces the chain map at the Q is equal to 1. Q is equal to 1. That's why. But this triangle is mapped to these edges. In this case, it's just mapped to 0. Because the dimension is different. Q is equal to here 2, but here Q is equal to 1. Therefore, it's just mapped to 0. That's how the signature map. So this断矩映射诱导这个诱导这个面复型的映射。And then you can easily check that this You can easily check like this. Easily check. They commute with this boundary map. So then the chain map is the following. So the following. So if you have the so FQ and F1, F3. So at each degree, they have some homomorphism from K to K prime. Oh, sorry, this is F. Sorry. Homomorphism. So each chain group is some abelian group. And you have a homomorphism as abelian group for F. And then if they commute means in the sense of the distance. With boundary map, this is called a chain map. It's called chain map.单处映射。如果交换的话，映射被称为这个是单处映射。So that's the case. So since if they commute, okay, if the D is inside the kernel, HQ of K, then F star of Z is also HQ prime. HQ K prime. Okay. So since the boundary of Z is equal to 0, F boundary of Z, the FZ take boundary is equal to F boundary of Z, and which is boundary of Z is equal to 0. Okay. So therefore F0 is equal to 0. So therefore, FZ is also inside the kernel boundary. Okay? Kernel boundary. So therefore, if they commute, they will induce the homomorphism between the homology group. 统调权的映射。Okay, and the question is, so this is homomorphism usually, homomorphism. So the question, when does it become isomorphism? 同态. Okay. So when does it become isomorphism? So to answer this question, we need to introduce so-called homology. So to answer this question, we need to introduce the notion of homology group. Okay. 这是同路。So if you have the two map, look, this is the question. When this map is a 什么是或这个映射是同态。So 同论是 so if x and g map x to y is the 两个变数连数映射 a continuous map 连数映射they call it the homotopy if they exist. The map x cross 0, 1 to y such that So if they satisfy this one, but for instance, if there exists something, say circle S1 is mapped to Riemann surface like this one. F is mapped to something like this one. This is the image of the F, and then another map is something like this one. Okay. So they are continuously deformed. Like this one, or the opposite way. Maybe it's okay. F is red and G is the yellow. You can easily deform. So when t is equal to 0 is the red one, and t equal to 1, this is the yellow. Okay. However, if there is a situation something like S1. Like this one. So this is F, and then G is something like this one. Okay. Can you deform yellow to the red, or red to yellow? I mean, if you try to deform it, somehow this yellow line has to just circle around again the genus, right? That cannot be done by a continuous map. You cannot deform it by continuous map. So therefore, they are not yellow and orange is not homotopy. Okay, so that's the notion of tone. And then x and y is 同路等价. 同路等价 is homotopy equivalence. it exists F such that G dot F is homotopy equivalent. So here we just write down the F and G are homotopy equivalent like this. You just denote like this thing. F, G are identity of F. F dot G like this way. So X and Y are homotopy equivalent. Okay. And then people just write down the X, Y are like this way. So okay, any一个例子 Rn is homotopy equivalent point. Okay. How do you show that? How do you show that? So let's F is Rn to point such that any point is mapped to point, and G is point to Rn is the point to 0. Okay. So this is the case. So there's Rn, and there's a homotopy saying that the homotopy from such that X and T is mapped to Homology state. Okay. If you do that, when t is equal to 0, there's the origin here, 0. And there's a point x here. When t equals to 0, it's just identity map. T equals to 0, so x is mapped to x. Okay? But when t equals to 1, x is mapped to 0. So it just map between these 2 points. So t equal to 0, like this thing. Okay. Okay. So like this way. So this will induce the homotopy between Rn and then point. Okay. Everything is just a causal 空间。So 这个 Rn 被称为这个 contactable space。科学空间，科学空间。So therefore, so identity of Rn is homotopic to the Rn is mapped to point. So both Rn and point are homotopy equivalent. So therefore, homotopy equivalent means does not preserve the dimension. So one is n-dimensional, the other is zero-dimensional. The homotopy equivalence does not preserve, not necessarily preserve the dimension of the space. Another example. So you just get rid of point in Rn is equivalent to Sn minus 1 here. That's the case. So in Rn, you just get rid of point. You just get rid of a point. Okay. Then any point x the point x and then t is mapped to so you can take such a map. So if you take like this way, so it's just norm of this one. So you just point to x. So there is sphere surrounding the origin. Sphere surrounding origin. Okay, and then it just map between these two. Okay, this is x, and this point is x mod absolute value of x. So that's how you can map between these two. So Rn, just get rid of point, it's homotopic to Sn minus 1. Okay, is it okay? And then the theorem, saying that if x and y are homotopy equivalents, so the homotopy equivalent, then okay, homotopy is then f star HQ of x and HQ of y are isomorphic. Okay. So this 这个同路单价的空间居于相同的同调圈。Okay, so that's the case. So that's the case. Maybe I should do. I should mention that this will form. So this homotopy equivalence is formed the equivalence class. So for instance, if the before just saying this, showing this one, if the x and the y is the homotopy equivalence, for instance F0, G1. Then so F0, F1, and G0, G1. Then this means that the F0 dot G0, G1 dot F1. Okay. Is the homotopy equivalent. That's very easy to show. There's a map between F such that the X and the Y are 0, 1 half is 1, and then G such that the Y cross 1 half 0 is equal to 0. And then if you combine 1 half 1, sorry. These two continuous maps, you can show that F0 G0 is homotopy equivalent to F1 and G1. Okay? So therefore, if X and Y are homotopy equivalent, and Y and Z are homotopy equivalent, that means the X and Z are homotopy equivalent. Okay? So therefore, they will form the equivalence law. And then, so these two, this is if the homotopy equivalent point is called this contractile space, and here this is called deformation retract. So this map is open for deformation retract. Deformation retract means all the point is just shrinks to the another S and -1 sphere. Okay. This means that the so in this map, so if you just restrict this H restricted to S n -1 is just identity of S n -1. So if you restrict yourself to this sphere, the point doesn't change. Okay, point never move, even though away from the point, you just keep moving to the sphere, but at the point on the sphere doesn't move at all during this 0, 1. Okay. So therefore, space is deformed to the sphere. That means deformation retract. Okay. So this is the homotopy. We introduced the isomorphism homology group. Okay. 诱导 so the 同路诱导统调权的isomorphism 相同同态。Okay. So let me show this one a little bit. Okay, suppose let me share. So suppose K and K prime is the synthesis, and through the map F, so K cross I and K prime. K prime is the simplification map. Simplification map, and then so let's take the f0 is just f of t equal to 0, f1 is equal to f t equal to 1. Okay. You just restrict yourself the f is at the t equal to 0 case, and then f1 is the t equal to 1. Then this will induce, in fact, so this is really a homotopy. So f0, and this means that the f0 and f1 are homotopy. So then f0 star and f1 star is the induced is isomorph, the same, is identical. So this is the theorem I want to show. Okay. So this means that if the x and the y are homotopy equivalent, so its f dot g is identity, right? Identity of x, and g dot f is the identity. F dot g is the identity of y. So this means that the f dot g star is the identity is homology group. Okay. Identity. So since the f dot g is just induces the identity of x, so therefore identity of x is just induces identity of homology group. And the g dot f is just a g star. Okay. So this, and also the same, is identity. Okay, so this means that the f star is mapped to h of x to h star of y is the isomorphism. So that's what it means. Is it okay? Do you agree with me? And also, G star is mapped to so this is the inverse of f. Inverse of f. Okay, if we can show that one, so this means that the if the x and the y are homotopy equivalent, then homology group of x and y are isomorphic. That's why. So let's show this one. So let's suppose. So let's consider K. K is something like this one. Sorry. K is here. K cross I is something. Okay. So K is equal to, so this is K cross 0, K cross 1. Okay. And this is the I. And then we call this A0 bottom, A1 bottom, A2 bottom, and here A1 upper, A0. Upper, A1 upper, A2 A2 after. Okay? A2 overline. This is overline, and then AI underline. We call it like this. And then we map D. K cross I, such that the Q is mapped to sum of sorry. K is the Q plus 1 of K plus I. Okay? So now, so the degree is just increased by 1. So after. Okay, like this. We define like this. So here, so you just have a 2 copy of I, so therefore it just increased, the degree is mapped to. So for instance, if you have a A0 and A1 is mapped to, one is the A0 bar, A0 bar, upper one, A0 lower one, A0 upper one, and A1 upper one, minus A0 lower one, A1 lower one, A1 upper one. Okay, so it's mapped to like this. So for instance, so this one and this one minus this one and this one. Okay? Is it okay? So minus yellow minus red minus yellow. That's a map we just constructed. So okay. So one simplex is mapped to linear combination of 2 simplex, like this. And then you can show the Z. So let's continue Q. Is mapped to like this. So like this one, you just map like this one. Let's look at this one. Let's look at this example. So boundary, so let's suppose first look at this first one. D and boundary. Okay. Let's take a boundary. D of, so this is D1. So A0, A1 is mapped to these two simplex. Okay? And then next you take a boundary. Okay? Take a boundary. what's left is that the what's left is so if you take a boundary of this red one, what's left is literally the boundary of this red one. Okay? If you take a boundary of this one, what's left is boundary of this one. Okay. Okay. A1, A0, A1, A1 bar. So therefore, if you take the boundary, if you take a boundary of this one, they cancel in the middle. And what's left is this, literally this. So, literally these two. The boundary of this, the rectangle. On the other hand, if you take a boundary first, what's left is A0 and A1. Okay. The boundary of A0, A1 is just that A0 minus A1. Okay. So these 2 points. Okay. Then take D. If you take a D of this one, what's left is A0, A0 minus A1, A1. So this is exactly did I make a mistake? This is exactly purple. This is a purple part. The purple part. Okay. And then I made some sign. I made somehow the sign wrong. Okay, so the blue one is the opposite. Sorry, blue one the opposite. The orientation is wrong. Sorry, blue one is wrong. Blue one is the opposite in direction. That's a blue one. And the purple one is the opposite orientation. Okay. So therefore, the both sides cancel each other. Purple and the blue one cancel each other. Okay. And what's left is this and this one. Is it okay? So purple and the blue one at the side cancel each other. Okay. So therefore, what's left is the bottom one and the upper one, which is of the original one. Original. Is it okay? Original is A0, A1. So the bottom one and the upper one. So this is exactly the statement I made here. You start with the Q simplex and take this combination del D, D del. Then what you get is bottom one and the upper one of the original. So you just have original on the top. That's what I mean. Okay. Then you can show up the. So if this one, if this one is the so Z is marked. So this means that Z is marked to the bottom one plus minus the upper one, and then if Z is inside a kernel or boundary, then kernel boundary, then this one does is kill the z. So therefore, what's left is down q plus 1 dq is mapped to z mapped to d bar minus d bar. And then, so if you just combine this original f, so f is the map from k 0, 1 to k prime. Therefore, we can just combine the first k is mapped to k plus I by this del d plus d del, and then you just map the f k prime. So you just compose the two map. If you two map, then f del d plus d del d is equal to f. So now z is assumed to be kernel of dot. So and this is mapped to so therefore this is f0. Star z minus f1 star z. Okay, so just like this. Okay, is it okay? Okay. And we already knew that they commute f del and then del f is equal to del f. They commute. So therefore, this means that this is equal to del f d. Okay. So therefore, the difference is just the exact form. Okay. Image of that. Do you understand? So therefore, as a homology group is the kernel of del and the image of del, right? Okay. So the sense the difference is just the image of del. So therefore, they are isomorphic inside a homology group. Do you understand what I mean? So this is the image of del, right? So the difference is just that. Okay. So f0 star z minus f1 star z is just the sum del of a. Is that what I mean? Okay. So therefore, as a homology group, they are saying the same element. Okay. So the homology groups they are the same element. Okay. So therefore, f0 and f1 star is just mapped to the same homomorphism. So that's the consequence. Any question at this moment? K times I is just a.
I can understand what you said, but K times I should be complex, and I'm wondering what's the.
Oh yeah, K times I is a complex. So we just have the so any path is the how to say we need to take some Good question. We need to take appropriately subdivision, like this way, and like this way. I think it's not. Let me think. Yeah, so we need to take like this way. Yeah. I think that's enough. So this means that you need to take AI and then I think what we need to do is something like so the simplex subdivision can be done by zero I and I plus 1 q like this. We can take such a simplex like this. Always the first lower indices have a underline, and then upper like how to say higher index has a overline.
I mean, A high afterline, not A high plus 1.
No, it's AI.
AI plus 1. Yeah. So A0, A1 is just like this, right? And also A0, A2 is like this way. So
we just define the Q signal. And I let you know. It's not sufficient to only define the Q signal. We should define syntax and
that's true. That's true. Maybe what I meant is that AI1 or AI say K AI K plus 1 AIQ. So this is simplex, or like this one, when I want. That's fine. If. So that's the subdivision.
K times I should only one dimension more than K. K times I is just one dimensional more than K.
That's true.
But in your nation, you have a lot.
That's a subdivision I just yeah. Okay. Okay, any question at this moment? Okay, so what does it mean? So what does it mean? So as I mentioned, so this is a proof of the schedule proof of this statement. If there's a homotopy equivalent of the map, we induce, oh sorry. It's mapped the isomorphism between the homology group. Okay? Not isomorphism. So the same homomorphism between two homology groups. This means that if the two spaces are homotopy equivalent, then this means that the x and y are homology groups are equivalent. The isomorphism. What does it mean? So direct consequence of this one is, for instance, this guy. So they're homotopy equivalent. Rn point is a homotopy equivalent. So this means that the H star of Rn or T is an isomorphic to H star point of T. Okay. So what is the homology group of point? Homology group of point is what? So this is isomorphic to C when Q is equal to 0, but otherwise 0. When the lowest degree Q equals to 0 means there's a connected component. So point is just a point of boundary point is 0. Therefore, this is the generator of the 0th degree. Okay. So this is a case. Okay. And then if you change R quotient is just R. R. So what's this? You already saw this one. What is it called? What is it called? You already saw very similar statement in before. Good. Topology. So Differential homology. Like this. It's a very similar statement. So that's concurrent. This is the concurrent. So you already see the relation between homology group and Differential homology. The same thing. So what does it mean about H star of Rn of 0 is safe. Okay. And what's this? Do you remember what is it about? So what's this?
Okay, equals 0 minus
Good. Okay. Okay. So this is intuitively, you can understand. But for instance, R Sn minus 1 is just a, say, so you have R n minus 1. There's a okay, disk. There's disk n minus 1. There's disk here. Okay. Disk here. Okay. So disk RD is just X inside of R n minus 1, such that the X is less than or equal to 1. You consider such a space. And to create Sn minus 1, you just put all the boundary to be a point, shrinks the point. Do you understand what I mean? So for instance, S2. S2 is just disk. You have a disk. And if you put all the boundary to the point, it's called one point compactification. You get the Sn. S2. Okay. S2. So all the boundary to the like a south pole. Okay. And then this disk is just cover entire sphere except this south pole. Okay. And it just shrinks, the boundary shrinks to the, it's like a 饺子. So when you create a 饺子, you create this key, okay? And then just put something inside and just wrap it up. Okay. So that's one point complication. So if you take a boundary of this one, boundary of disk, you just have a boundary, right? Boundary is n minus 2. But the boundary is just shrinks to the point. Okay? Shrinks to the point. So therefore, the boundary of this one is just the nothing. Nothing. Okay? So that will create the cycle of the n minus 1 degree. N minus 1 degree. Boundary of this disk, if you just do the you identify boundary of this disk is the point. Okay, so then it just maps to the point. So therefore, C n minus 1 boundary and C n minus 2. So just n minus 2 to n minus 1 to n minus 2. It just this disk is mapped to the point, which means that is not inside n minus 2. Okay. So therefore, this boundary map is just become 0. So therefore, this is cycle, n minus 1 cycle. So that is the element of R. Okay, that's an intuition. And then Q equal to 0 is just how connected component. Connected component is just one connected component. So this R, n minus 1 degree R is just it's fundamental class. So entire S2 you can consider. Let's compute this the homology group of Sn by a different method. Wait, I think it's a good time to take a rest. So another way to compute this Sn homology group is using so-called Meyer-Beator's exact sequence, but I think it's a good place to take a break. Yeah, let's take a break. 10 minutes break. Okay. Shall we review? So this is an intuitive way to explain the homological properties and the sphere. But there's another way to do that. So-called major. It's exact sequence. So this is called正和序列。So first of all, I will explain what's a 整合数列。整合数列 is the if you have a billion group. Like this. Like this. If you have this the schema, the conventional linear map, if kernel Fn is equal to image, let me write here. Kernel Fn is equal to image of Fn. n minus 1, then this is called short exactly. Long exactly. This means that you can have so these are Boolean group. A stands for Boolean group. So you always have like this, right? So this is the image. So here is image of fn plus 1. Sorry, n plus 1 is equal to kernel of fn. If this is the case, f always it's called exact sequence. Okay. Is that okay? So for instance, the so this is different from chain complex. Okay. Chain complex, if you remember, chain complex usually chain complex we have n plus 1, n, and cn, and so on. Okay. Maybe it's better to call it Q. Okay, it's okay. It's just a method. So boundary map. So the difference between kernel image or homology. So kernel and image, the difference is usually, so this is image of boundary and the kernel of boundary, and the difference is the homology group. So difference is homology of whatever space X. Okay. So that was the case. But here we always image is equal to kernel. Let me give you an example. So this is times 2. And then this is the mod 2. So for instance, it has only 0 and 1, right? And the times 2, it's mapped to 0 and 2, right? So it's a 3, 2, 1, 0. So Z4 is 3, 2, 1, 0. But this 0 is mapped to 0, 1 is mapped to 2. Okay? And here you have 0 and 1, right? So if you take a mod 2, so 3 and 1 is mapped to like this. Okay? Mod 2. But 0 and 2 are mapped to 0. So in this case, image is always kernel. Is it okay? Image is 0, 2 is always mapped to 0. That is the meaning of image equal to kernel. Is it okay? Is it okay? So another example. Another example Z. Maybe E to Ty. So this is the inclusion. The inclusion. And this map R star is just R star is the multiplication group, which is the R as a Z. It's just multiplication group. And just get rid of Z. So you have an element and the Y. So you have in R. you have a multiplication, right? Like this. You have a multiplication. And then if you set some integer n, it's just inclusion. N is mapped to, sorry. So of course the identity is just 1. So here it's just identity is just 1. Identity element is 1. So therefore, so n is mapped to n, and then e to the 2 phi I n is equal to 1, always, if n is integer. So everything is mapped to, sorry, I think R is not good. C is bad, sorry. C is bad, sorry. C is bad. So this is another. This is called, if there are only 3 elements up here, it's called short exact singlet. Okay, so that's those examples. And then may be torus sequence is as follows. Okay, and then k is equal to k1 half k2. Okay. Then we just consider the following. This is inclusion, and this is another inclusion. Another inclusion. J, K. And then we just use the map. I call it the phi is mapped to HQ, K prime to HQ. So just suppose those inclusion or simplification, then that will induce the homomorphism between the homology group. So Z prime is mapped to I star Z prime minus J star Z prime. Okay. So I is the inclusion of K1, and then J is the inclusion of K2. The same thing, let's go psi. Is mapped to K star Z1 plus L star Z2. So every simplification map will induce the homomorphism between the homology group. And the homology group is abelian group, you can just add it up. at a time. Okay. So then, so given the Z, C1 plus C2, so this C1 is H1, HQ, K2, like this one, HQ of K2, like this one, then you can define the boundary number of a delta. HQ of K is up to HQ minus 1 of K prime. Okay. Such that the Z is not the boundary of C1, it's minus boundary of C2. Okay. That's the map we define. So the boundary of Z is equal to what? 0. Because it's inside homology group, it should be 0. So therefore, this means boundary of C1 plus boundary of C2. If you add them up, you should get 0. Okay? So this means that the boundary of C1 should equal to minus boundary of C2. Okay? Is it okay? And it turns out that this delta is independent of the decomposition. Okay. So here there is a choice how to decompose. Choice. There exists a choice, but this is independent of this choice. So that's you can show that. I'm not going to show exactly what's going to happen. Then one can show that follows. I need to write down. So you just increase the degree one by one. Okay, like this. So this is the Mayer-Vickers exact sequence. So let's look at them one by one. So Z prime is mapped to I star Z prime and J star Z prime. Z1, Z2 is mapped to K star Z1. So you just add it. So if you map like this way and then you just add them up, they cancel, right? Z prime, essentially this is Z prime minus Z prime. If you add them up, you get 0, right? So therefore, the image is equal to kernel of this map. Okay, this is phi, and this is psi. Okay. So this image is equal to kernel of this map, psi. And then if you map Z1, Z2 like this way, okay, and then take a delta. This is delta. This is delta, and the phi, and the psi. If you map like the Z1, Z2 like this way, okay, and take delta. This means that you just take the del of Z1 is equal to 0, or del of Z2 is equal to 0. Because it's inside homology group. Okay? So therefore, this image of psi is a kernel of del. Okay? Kernel of del. Okay? Is it okay? So the kernel of del means that the del C1 is equal to 0, right? Okay. Del C1 equal to 0, which means that the C1 is inside a homology group of K1, or C2 is also inside a homology group of K2. So therefore, image of psi is equal to kernel of del. Now let's look at the image of del. Image of del is just a del C1. Okay, del C1. And then put the psi here into here. Oh no, sorry, phi here. Okay. What is that? How to see that is the homology. Oh yeah. Okay. So it's just that Z goes to del C1, boundary of C1. So therefore, here is just boundary. Okay, boundary. So therefore, so it's just a boundary of something means the 0 inside a homology group. Okay? 0 inside a homology group. Do you understand what I mean? The boundary of C1 means that it's trivial class in a homology group. Okay? The homology group is the kernel of divided by image. And if it is the image of boundary, so this means that it's trivial inside a homology group. Okay? So therefore, image of del is the kernel of psi. Okay? Kernel of psi. That's what it means. Fine. So therefore, this is always kernel. So this kernel of psi is equal to image of del. And then kernel of delta is image of psi. And then kernel of psi is equal to image of phi. Okay? Always this is the case. So this means the exact sequence. You can see exact sequence. This is an exact sequence. Now let's compute the homology group sphere by using this one. Homology group of sphere. Any constant is okay. Z. Okay. So let's do that by induction. By induction, so this one, suppose this is true. Okay. And then, so we just, like this one, so this is Sn, and then this is K, and Ky is northern hemisphere, and southern hemisphere, and the intersection is this one. Intersection is K prime, which is Sn-1. It's an equator, which is the n-1 sphere. Okay. Let's consider K1 and K2, and the intersection is just a middle one-dimensional lower sphere. Okay. And if you just add them up, you have a sphere N. Okay. That's the situation. So let's consider, in this case, so we know this one is the sphere, is the, we already called, by induction, this is Z. Okay? But we already know, so K1 and K2, what's the homology group? What are the homology group? K1, K2. What are K1, homology group K1, K2? K1. It's just disk, right? So it's just disk. It's a contractible space. Disk can be contractible, right? So it's the same as Rn. So you can use a Poincare number. So everything, so H, Ki, T, otherwise. Okay? So then this is 0, then this is 0. Okay? And everything 0. The apart from that, everything 0. Okay? And this is Z. We already know this is Z, and this is Z, and this is Z. Okay. We already know this is 0 and 0, and this is 0. Okay. So this should be exact sequence, which means the kernel should be image. So Z goes to 0, right? So here everything goes to 0. Okay. So therefore entire Z is a kernel of this phi. Z goes to 0. Therefore, image should be Z. This image should be Z. Okay? But here, 0 is mapped to here, 0. So therefore, there is no kernel. So this means this has to be Z. It has to be isomorphic. It has to be isomorphic. Okay? And here, of course, this should be 0. Everything should be 0, except the last one. Last one, Z goes to Z plus Z. In fact, A is mapped to, okay, N is mapped to minus N. Okay. Anti-diagonal. So it just mapped to anti-diagonal. And if you take a quotient, it should be Z. It should be Z. So therefore, the Q, sorry, I told you wrong. This should be N. Okay, 2-dimensional field. a q-dimensional sphere, q minus 1 dimensional sphere. Then let's go n it should be q minus 1. That's fine. So then, so therefore, what means that this one should be Z when n is equal to 0 and the q, otherwise 0. That's one way to compute the homology of sphere by using Meyer-Diedrich exact sequence. 尖数列。Okay, any question at this moment? Any question at this moment? So this is one way to compute the homology of sphere. So the kernel, so image, non-trivial image, just for instance, n, and then you can take n. 答案我无所谓。Okay, any question? So let's consider now. Let's consider 这个善同调群。So 现在我们只下了我学习了同调群。同调群是 a medium group or like a vector space. If you like a 向量空间，所以可以考虑这个对语空间，所以homology。上同调。上同调群。哦 ，OK， so DQ 个有链群或千轨。Or maybe, okay, any ring is okay. So R can be considered Z, Q, like this. So so it's just one. So this will satisfy the 线性函数。Okay. and 然后 U 与边界算子，然后now it just increased by degree. So notice that. So the lower CQ plus 1 down. So there's a parent between these two, natural parent these two. So therefore, del f of c is equal to f del c. So this is an element in f, and then here the c here. So del f is paired by c. If this is the case, the boundary of c is paired by f. Is it equal? That's how you define it. That's how you define it. And then, of course, del square f c is equal to f del c, and f del square c is equal to 0. Del square is equal to 0, so therefore del square f is equal to 0. So this means that del square is equal to 0. Okay, so then we can consider the following thing. So the chain map is like this way. Chain group is on the other hand, like this one. Okay, like this one. So now it's just increasing degree. And then you can take the homology group of homology group. We can again just kernel down divided by image of down, like this. And then we can have natural parent. Okay. So you can have a natural pairing. Okay. So you have a parent. So the C and the F is not to FC. It's a natural pairing between homology group and cohomology. And then if the R is a ring, if R is ring, also field, sorry. R is a field, Q or Z. One can show that the H, Q, it's just dual. It's just dual. So which means that the R is a field, so which means that it's just dual. It's just dual. So for instance, the H, so this can be seen that we already saw this example. Where did we see? Today we saw this example. Where did we see? Do you remember? This is example we always saw it. Origin, 한국, 이거 is. Homology group is dual of cohomology group. Concurrent. So H, Q, R, M, R. Now, for instance, drum, it's just that R, Q equal to 0, and the Q is otherwise. Okay. But that is also isomorphic to like this. Okay. So this is literally dual, right? So R dual, home R to R is just R. Okay. Is it okay? So now for R is mapped to R. So this is another example, for instance, H star, HQ. So now for HQ of Sn, like this way, and this one is isomorphic to like this. That's it. Another way of doing it. However, in general, this is not true. This is not true. This is not true. If you use Z coefficient, this is not true. Because it's not field. Do you know field and the ring, right? Is it okay? Do you understand field and the ring? Field you have an inverse. But the ring, not necessarily, you have an inverse. So to get this one, to get the information called homology group of Z coefficient from homology group, you need a so-called universal coefficient system. So I'm not going to say anything about the universal this quotient theorem. You can just refer to Hatch's group anyway, Wikipedia, whatever, whatever you like it. You can check that. So the important thing is that so if the usually this HQ contain the torsion group. So for instance, so we already saw that the HQ of RP2 of Z. Do you remember? Okay. And this Z2 is a bit complicated. What are the deal with Z2 and so on? So those are complicated things. So that makes complicated. So to use to define the homology to call homology, with Z coefficient, you need to use so-called universal coefficient. Which I'm not going to say anything about it, because we're not going to use that. And then, so here it's very similar. So as you already knew, so this 这个相同调的定义，非常相同，和 drum 相同调，非常像。So there's a theorem saying that drum定理 drum is called homology. It's actually a drum homology, isomorphic to drum homology. So when K M is a homology. So the drum cohomology is equivalent to just cohomology, which we define like this, the simple-Shah cohomology. And to show that you need to use so-called check cohomology. I mean, check cohomology, I'm not going to introduce. So that this proof is given by Morita's. I mean, if you're interested, you can just consult Morita's book. So here, right hand side, when you define the drum cohomology group, we use differential form. Okay, differential form. Left hand side, we just use the dual of the simulation homology called chain or called chain group. Okay. Dual of chain group. So the construction is different, but they are isomorphic. So the okay. The homology group we can have. So here we can have some cycle areas, so you can just define. So which product we can have. So this is HQ drum, then this is HP of drum, HP plus Q drum. Okay, so that's. And then what are the corresponding operations here? What are the corresponding operations here? So we can do the same thing. So the phi and psi do the same thing. So we can define so cut product. Cut product. Okay. So this is okay. So then okay. So AP we can define like this. Sorry, I think that should be. We can define the cut product like this. Yep. So that's the case. Is it okay? Sorry. Maybe so. Oh, field R. Sorry. So this is if it is a field, they are isomorphic. They are isomorphic. If it is Z, that's isomorphic. And maybe you can also consider C too. So this is a field. So the field in Chinese is T, you say? 域区域的区域 The field in mass in Chinese. Oh.
数学常用搭配 field 等于 number field 等于数据等于 field 向量场 field axiom
I see.
是公理
I see. I don't know. So ring is what? Is it like this? Okay, this is right. Thank you. Okay, so the field, if it is a field, there you sorry. So there, if it is a field, sorry, I think I should follow. So this is I wrote D, but that's not true. So we also include C, often called C quotient. C quotient, especially. Okay, so here you can consider as a vector space. So therefore H star of M R is cut product. Here you have considered the vector space. So it's a abelian group. So you have addition, and this one, the cut product will give you multiplication. Multiplication between HP and HQ will give you HP plus Q. So therefore, this is to give you ring structure. So 换结果。ring structure. In particular, so for instance, H star, okay, of, for instance, CP and the C coefficient is always C when, sorry, Q. Q is equal to I. When the theta are there. Okay, in fact, and then this can be understood as the ring structure is C x mod x to the n plus 1. As a ring. This is called a polynomial ring and a quotient by ideal x to the n plus 1. It's and then x is a generator of H2 of CPN. X is the CPN is a complex projective space, and inside always generator is the spheres inside. So this is the generator of essentially isomorphic to CP1. So this CPN always has a submanifold CP1 inside, in fact, and then that will just create the ring structure. So this means that it's a ring generated by 1 x squared to the xn. So those are like polynomial, like a polynomial, right? It's with one variable. But if you multiply x to n plus 1, this is identified to be 0. So that is called a polynomial ring. So this is a ring structure one can have. This is one example I can just show you. Oh. And that's the case. Any question at this moment? And then concordiality. So the M is compact. Okay, closed. Oriented. Connected. The manifold. n-dimensional manifold. And if you have a cycle n, is mapped to, you can define the omega is mapped to A. The drum cohomology such that always like this way. Like this one. And this is always isomorphism. That is a concoidality. Okay. So we already saw the drum cohomology. So here this one is by Hodge. Using Hodge term, this is also n. Sorry, k. K's degree drum cohomology. Therefore, this one is isomorphism between h and minus k. That's the case. So they're all isomorphism. So in general, so if it is cross-oriented, connected n-dimensional manifold, we have HK. Okay, so that's the case. So those are concordant duality. Concordant. Concordality. So concordant. Do you see? And then using so that given a cycle N2, so you can just take a dual cohomology group in a spin, dual cohomology group. So this is for intersection number. Check intersection number.交叉，这个是交叉数 intersection of 交叉 Okay, let's look at the example. So torus homology group we already saw last time. Okay, homology group we saw last time like this one. Torus is like this one. So this is S1. So let's call this one is the S11. And then here S12. Okay. And then you can do the integration. So the integration of S1 by S11 d theta 1 set to pi. Okay. And then here you can have another S12 d theta 2 to pi. You can do that. So those are the homology group. So this one is S11. The T2 and this is 1. So homology group in R is just a nothing function. It's just function, constant function, and this is d theta 1, and then d theta 2, and the R d theta 1 wedge d theta 2. So those are generally the homology powers. Is it okay? In drum cohomology. Drum cohomology is differential. So those are generated. And then under the peculiarity here, what is the dual of S1, S11? What is the dual? What's the dual of this guy? Dual of this guy? Either d theta 1 or d theta 2. H1 is mapped to H1. H lower 1 is mapped to H upper 1. What's the dual of S11? Either this guy or this guy. So peculiarity hk is mapped to hn minus k, right? Now k is equal to 1. Is mapped to h upper 1. Okay. So the differential is given by so what is the dual of H11? So this is a volume form, the topic of homology class. Topic of homology class. So in this case, like this one, D01, 2 pi, and which this one. So this can be treated as omega. This can be identified omega here. This identify A over there. You understand what I mean? Even if you put the d theta 2, d theta 2 does not see this. D theta 2 only see this red one because it's a dual to S12. Its angle of this red line is theta. Angle of yellow line is theta 1. Okay. So therefore, so the S11 d theta 2 over 2 pi. S12 is dual to d theta 1 over 2 pi. Like this. Okay. So those are congruency. Is it okay? Okay. In any case, so therefore, so intersection number of S1 not S1 2 is D2 D01 2 pi, which is equal to 1. Okay. So literally, so yellow and red are intersecting by 1 point. Okay. So therefore, intersection number is just how they intersect the cycle. One cycle intersect each other at 1 point. For instance, if you just the self-intersection, if you S11, S11, and then you get the d theta 2, d theta 2, right? Then this is equal to 0. Because I mean, d theta 2, which d theta 2 is equal to 0. So therefore, no self-intersection. Okay. That's what's happening. Okay. Fine. Now let's look at this example. So see, R quotient is the same. R is always the same. R quotient is the same. If it is R, this is the ring is like this. Okay, so as you can easily see, so this is the essentially R. And then you can always pair, then by Hodge duality, you can always pair these two. These two. Those are Poincare duality. Okay. So a compact compact oriented, closed oriented connected n-dimensional manifold, always 0 and then top cohomology is R because of the point cardinality. Compact oriented. But for instance, if you look at the homology group Q of M R, definitely this is definitely true. Q is equal to 0 and the n dimension. So the lowest degree is Q equal to 0 is generated by connected component, and the top degree is generated by fundamental class M itself. So this n is generated by M, and this is generated by point. And they are related by point cardinality, so you can see them. And in fact, x to the k, here you can identify still to x to the n minus k. So that's the, you can see the duality between them. Okay, so that's the point cardinality and the intersection law. Okay, so let's stop here. So today I introduced many things. A homotopy equivalent, a homology group, cardinality. The next time I will talk about the fundamental group and so on. Okay, let's stop.可以查。